All right, today is lesson 7.2, kind of switching things or changing things up a little bit. You did some systems of equations yesterday. What we're going to do is we're going to use a matrix, and eventually the idea is this matrix will help us solve a system of equations a little bit faster. So our learning target is I can find sums, differences, products, and inverses of matrices, which that's just the plural form of a matrix. And then I can find determinants of matrices. So we're going to teach you what a matrix is and then have you do a bunch of operations with it. The cool thing is, for the most part, because matrices are made up of real numbers, they're going to take on a lot of the properties of real numbers too. Not all of them, but a lot of them. So the definition of a matrix. So, brand new to you, I know this. It says let m and n be positive integers. Okay, so an m by n matrix, okay, read m by n, is a rectangular array, which an array is just a way of organizing. M horizontal row, so what it is, it's m by n. So we always name matrices by how many rows they have, comma, or I should say times or by how many columns they have. Okay, which is kind of weird. You know, I always think like this way by this way, you know, 4 by 5 or a 3 by 2. It's actually this, it's how many rows by how many columns is how we name this one. So try to get that, change gears if you think like me. We use the shorthand notation, A, and then however many rows it might have, however many columns. Now, in this number I and j, that tells you the location of it. Okay, the first number, so like this number right here says first row, first column, second row, second column, mth row, first column. Okay, so that's like, think of it as like almost like a battleship board as you're looking at this. Certainly most of you played Battleship at some point in your life. If you haven't, I'm sorry, it's a pretty cool game. But yeah, so it's just an organizing numbers, real numbers, into rows and columns. And then eventually we're going to see that there's a lot of really applicable things to this. In fact, I took a graduate level stats course a couple years ago, and we used this in stats, and I had no idea until, I'd been teaching for, at the time, I think it was my 14th year teaching, and I didn't know that you use matrices in stats, but you do. So determine the order of a matrix. So the order is just what m by n. Okay, so this one, it is 2 by 3. So this would be a 2 by 3. That's the order. Okay, that's what we mean by order. So maybe try the next two out. Just write them down real quick, and then we can come back and unpause the video, and I'll have the answers on here. So try the next two. Just take a minute or two, or not even a minute, take 10 seconds, and write those down. Okay, and now this last one was a 3 by 3. We call that a square matrix. When it has as many columns as it does rows, that's called a square matrix. And there's a lot of things you can do with a square matrix that you can't necessarily do with other matrices. Now, addition and subtraction is about the way you would guess it. If I said, go ahead and add these, and I didn't tell you how to add them, you would probably guess the right way of doing it. So matrices of the same order can be added or subtracted by adding or subtracting their corresponding entries. Now what's important though, what's very important is that matrices of different orders cannot be added or subtracted. So these two up here, in fact none of these, take any pair of these, they could not be added or subtracted. For instance, if I said add these two matrices together, what's the corresponding part? Well, 1 corresponds to 1, 2 corresponds to 2, but then nothing corresponds to this 2 or that 3. Over here, eventually the 3 and the 4, though there is no third column over here, so it doesn't correspond. So you can only add them if they have the same number of rows and same number of columns. So for this one here, if I said add up matrix A plus matrix B, we always use a capital letter to name matrices. We use letters to name them. So this is matrix A, this is matrix B. If I said add them together, 4 plus 6 is 10, 10 plus 0 is 10, you kind of get the idea, 1, negative 1. And then over here, A minus B, and order matters. When you're adding, order does not matter, just like with real numbers. But when you're subtracting, order does matter. Okay, so on this one, I'm doing a minus b, so 4 minus 6 is negative 2, and then 10 minus 0 is 10, negative 5 minus 6 is negative 11, 2 minus negative 3 would be a 5. Okay, so addition and subtraction is about as easy as it sounds. The next one, if we wanted to multiply by a scalar, okay, which this is different than multiplying two matrices together. We're not actually multiplying two of them together. We're taking a matrix, we're multiplying it by 2, 3, 5, negative 12, 1/10, whatever it might be. So a scalar is when you're distributing, okay? So if I said k times a, where a is 2, that's the same thing as 2a. Using the same a up here, what would 2a be? Well, double every entry. Okay, so 8, 20, negative 10, 4. If k was negative 3, that means you're going to take negative 3 times everything. So 4 times negative 3, negative 12, and then 0, negative 18, and 9. We can do different, we can multiply and add. So what if I said take twice a, then add it to b? We already have a or twice a over here. You could use these numbers if you want. Now, if we didn't have that, I would just say twice a, that'd be 8 plus 6, 14. Twice of 10 is 20. 20 plus 0 is 20. Twice negative 5 is negative 10. Plus 6 is negative 4. Twice of 2 is 4. 4 plus negative 3 is 1. So either way you look at it, it doesn't matter, since you already had this one. Okay, so those, I say those should not give you any trouble, what we've done so far. Okay, so order, just naming it, rows by columns, and then addition, subtraction, you add corresponding parts. If you have a scalar, which means you're multiplying the entire matrix by something, I think of that more as a distributed property and distribute it out to every part. Where it gets real sketchy here, really sketchy, is when we get to matrix multiplication, which means we're actually going to multiply two matrices together. And it's not how you would think, because I would guess you just multiply the corresponding parts, but that is not how it works. Okay, so here's our definition, and this is going to throw you off, and you're going to have to. It's one of those, you got to do it. Okay, so you got to work this with me, and if you got to pause 10 times through the process, pause. Okay, so it says let A be one matrix, and let B be another matrix. Now A is an M by R, so it has M rows, R columns. B is an R by N matrix. The product is what you get when you multiply, and I'm just going to show you. This is confusing, so maybe don't even try to read that. Don't even try to read that at all. But the result of this, if you notice, is going to be an M by N matrix. It's almost like the R's cancel each other out. Okay, so M by R times R by N equals an M by N. So on this one right here, the order of this guy is 2 by 3. The order of this guy is a 3 by 2. That means my answer is going to be, basically wipe these guys out, it's going to be a 2 by 2. So my answer is going to be a 2 by 2, but I'm going to leave a ton of space here. Okay, I'm going to leave a ton of space and we can simplify this. So what we're going to do, you take the first number here times this number. So it'd be 2 times 1 plus, now 1 times 0, so it's this column times that row. We multiply the corresponding parts and add them up. So 2 times 1 plus 1 times 0 plus negative 3 times 1. And that's going to be the first number in this matrix. So we can say that that is the location A11. So this would be 2 times 1 is 2, plus 0, minus 3 would be negative 1. Okay, so this is my final answer here. Now this one up here, I'm going to take first row times the second column. So this was first row, first column, now it's first row, second column. So I'm going to take 2 times negative 4, which I'll just put negative 8, plus 2 times 1, plus 2, plus negative 3 times 0, which is 0. So this is going to be a negative 6. Now, second row times first column is going to give me this guy. So the second row times the first column. 1 times 0 is 0, I'm not going to write it down. 1 times 0 is 0, don't even write it down. 2 times 1 is 2, that's going to be a 2. And what's left? Second row, second column. So this would be negative 4 times 0, I'm not going to write it down. 2 times 1 is 2, and then 2 times 0 is nothing, so that's just 2. So A, B equals this, and that's a notation for I multiplied A times B. Now, one thing that's confusing about matrices is with real numbers, when you multiply, the order does not matter. 2 times 3 is the same thing as 3 times 2. But what if I took B, I'm not going to actually do it, I can display that it's different just by showing you this part. B times A, well, B is a 3 by 2. If I took that times A, which is a 2 by 3, the result, so BA, would be a 3 by 3, which is obviously different than AB. So the order does matter when multiplying matrices. Okay? With real numbers, it doesn't. And I told you it's almost all the same, but it's not completely the same. Okay? So try, I know there's not a lot of room out down here, but try this out. Okay? So pause the video, try to multiply these together, and in a little bit, hit play and see if you got the right answer. Okay, so hopefully you recognize that they can't be multiplied together because these inside numbers have to match. So the number of columns has to match the number of rows here, or else you can't do it. This is a 2 by 3, this is a 2 by 2. Those numbers don't match, so this cannot be multiplied, so this is not defined. If I said what's AB, in this case it's undefined. Okay, so let's flip this guy over now. And we're going to talk about the identity matrix. Okay, so if you remember that there's in real numbers, when we say you multiply by the identity, well, that means it doesn't change the number. And well, 1, if you multiply any number by 1, you get itself back. That's what the identity matrix is. It's the matrix that when you multiply anything by it, you just get that number back. Okay, what it looks like, it says here, now it says the identity with n, which is, I should start out too, that the identity matrices, an identity matrix is always of the order n by n. So it's always a square matrix, and it always has a diagonal of 1s. Okay, so if it's I2, that would be a diagonal of 1s, a 2 by 2. I3 is a 3 by 3 with a diagonal of 1s. I4 is a diagonal, or is a 4 by 4 with a diagonal of 1s. Can you get the idea? And if you take any square matrix and you multiply by its identity, you get that same number back. Okay, but the thing is, all identity matrices are square, so in order to be multiplied by I, a matrix must also be square. It has to be a square matrix in order to multiply by the identity. So yeah, so if you take A times the identity or the identity times A, remember order matters here. Doesn't matter, whichever way you do it, you get A. Okay, and that's true of this identity matrix. We're not going to be able, we didn't get to doing enough of that because we kind of ran out of time this first semester. But in future math courses, this is really helpful to have the identity matrix. It's extremely helpful. We don't get to see it very much. We just didn't get to work with it very much because we only have a few days left here in the semester to talk about matrices. But I want to introduce them at least so you know what they are. Now the inverse matrix, so this is something different. The identity matrix is what you multiply something by to get itself back. You know, it's like multiplying by 1, you get the identity, you get the same thing back. The inverse matrix is the matrix you would multiply anything else by to get the identity. So if I'm talking about matrix A, its inverse is B, and if you multiply to A times B, you get the identity matrix. So this would be the result of multiplying them. Same thing if you did B times A. So order on this one, it goes both ways. So that is called the inverse. So if B satisfies this, then B is considered the inverse of A, and we could write it like this. So you could say that A times its inverse equals the identity matrix, which also the inverse times A would be the same thing. They'd all equal the inverse matrix. Okay? Now, most, but not all, square matrices have an inverse. There are some that don't, but it has to be square. So if a square matrix doesn't have an inverse, it's called a singular matrix. If it has an inverse, it's called non-singular. So singular just it goes by itself. You can't multiply by anything to get the identity. So let's try this out here. I'm going to give you a 2 by 2. So verify that these are inverse matrices. So we're going to multiply them together. We want to multiply both ways and see if we get the identity matrix. So since the second example on the front side was you couldn't multiply them together, try it out. And I want you to quiz yourself. Do AB first, and then do BA. Keep in mind, this is a 2 by 2, and that's a 2 by 2, so the result is going to be a 2 by 2. 2 by 2. Since we're verifying, we're hoping it's 1, 0, 0, 1, 1, 0, 0, 1. So, but try it out. See if you can get that to work. So I did this one first. I did A times B, because the order they're written is easier for me to follow. But I got 3 minus 2, which is 1. 6 minus 6 is 0. This is 0. This is 1. So that's the identity matrix. So 1, 0, 0, 1 when you simplify them. Now to do B times A, I'd like to rewrite this over here. So 3, negative 2, negative 1, 1. I rewrite it over here. That way I can follow the patterns. Okay, so try that out. Pause your video and try that out. And when I did that, I got 1, 0, 0, 1. So that both ways I multiplied, I got the identity matrix, so there I verified. So yes, those are inverses. Show that this matrix is singular and has no inverse. Okay, that's a little bit harder to do. So let's say this is A. So A equals 6, 3, 2, 1. And I'm going to let B equal, I'll just say X, Y, Z, W. I'm not sure what B is, but I want to show that it's not. You can't come up with one that works here. So let's figure out what A, B is. So AB equals, now this would be 6X plus 3Z. And then over here would be 6Y plus 3W. And then 2X plus 1Z. And then 2Y plus W. And if you look, kind of line these up here, I've got XZ, XZ, YW, YW. So there's something that's supposed to be happening here, and this is supposed to equal 1, 0, 0, 1. So 6x plus 3z should equal 1, but 2x plus z equals 0. What's going to happen if I took 2x plus z, which is supposed to equal 0, and I tripled that? So if I multiply this, it'd be 6x plus 3z equals 0. But up here, 6x plus 3z is supposed to equal 1. So can the exact same thing equal 1 and 0 at the same time? No. Same is true over here. If I triple this bottom one here, now 2y plus w is supposed to equal 1. If I triple that, it'd be 6y plus 3w equals 1. But right up here, this says that 6y plus 3w should equal 0. It's the exact same expression on both sides, but it equals 0 once and 1 the other time. It can't work. So this one does not work. This one is singular. Okay? Now with the determinant, this can actually help us figure out if it's singular. So you think, I don't want to do that every time. Good grief, that would take so long. You're right, you don't have to. There's this thing called the determinant. Okay, and so first off, with what we're doing, we're going to do the determinant. We can do it by hand for 2 by 2s. It's very simple. The determinant is going to be, if matrix A is A, B, C, D, the determinant of this would be AD, A times D, minus B times C. Okay, and as long as this doesn't equal 0, it has an inverse. But if this equals 0, if AD minus BC equals 0, it doesn't have an inverse and it's singular. So let's go up here and look at this. A times B would be 6 times 1, minus, and then B times C would be 3 times 2. 6 times 1, that's 6 minus 6 equals 0. The determinant's 0. So I could have done this and said, nope, that's singular. Now this is why, over here, this is a good reason why, but this is way faster. So we would like to be able to do that every time. But if we want to quickly find that inverse, okay, so our goal here is to find the inverse. The thing that you multiply by, A to get the identity matrix. Okay, we want to find its inverse quickly here. Well, the trick is find the determinant first. So AD minus BC, put that over 1, and then multiply by a matrix that looks different. It's matrix A but rearranged. We switched A and D, so A and D switch places, and then B and C switch signs. Okay? So if we do that, if we do 1 over the determinant and then distribute that, that's a scalar, times each of these parts once they've been rearranged, boom, that's my inverse, which is a lot faster than any other method. So first off, on this one, let's find the determinant of A. So determinant of A is going to be AD minus BC. So AD is 6 minus 1 times 4, which is 4. So that's 2. So I'm going to take 1/2 as a scalar. Now I'm going to rearrange A. I got to flip-flop these positions. So 2, 3. Then I'm going to switch these signs, -4, -1. So I'm going to take half of everything. Half of 2. So again, this is the inverse of A now. Now that I'm multiplying this out. Half of 2 is 1. Half of -4 would be -2. Half of -1 is -1/2. And then half of 3 would be 3/2. It is okay to have fractions in there. So don't freak out about that. Now, and that's for 2 by 2. So this formula, all of this is for 2 by 2s. Because notice, if I said for 3 by 3, take AD minus BC, well, what about all these other numbers? You can do it by hand. Because this year we're kind of short on time, I'm not going to do it by hand. I'm going to let us use the calculator to do this. So what I'm going to do, I'm going to show you how to put these into the calculator. So first off, if you want to put a matrix in, there's a matrix button. Okay, so right here, see matrix. To get matrix, you got to push second and then that button. This pops up, and it's kind of like lists. You need to edit if you want to change it. So I need to go over to edit if I want to put the matrix in. If I want to manipulate the matrix, then I'm going to use math and then choose a name. But right now I needed to edit, so I'm going to edit. This is a 3 by 3, so I got to change this to 3 by 3. And then put the numbers in. So 1, enter. 2, enter -1. Okay, double check you got them all in there, okay. So that's matrix A. Matrix A is this guy, which I know it says B, but we're just going to, because we're putting the calculator. Now if you want to do anything with this, you got to go second quit and get out. Whoops. I just want to quit. So now I'm back to my normal screen. Now I need to find the determinant of this first. So I want to take 1 over the determinant. Actually, no, let's just skip that. Let's just let the calculator find it. I'm going to let the calculator find the inverse. Now if I go to, second matrix, I'm back to second matrix, go to math, and I can find the determinant. I'm just going to go find the inverse. Actually, I think it's not even in this list. Yeah. Here's what I got to do. So second matrix, A. So right now it's saying, what do you want to do with it? I want to take the inverse, which happens to be that button right there. Okay, so it should look like this. What is the inverse? So the inverse of B would equal, and it did a lot of work for me here, 0.2, 0.2, -0.4, 0.5, 0, 0.5, 0.2, 0.2, and 0.6. So remember, what's so special about this? Well, if I multiplied B times the inverse of B, I would get 100,010,001, which is very helpful for what we want to do. Okay, so we'll talk about that in future days. So we're approaching 25 minutes. I apologize the video is so long. I think I told you we're kind of cramming stuff in before the end of the semester here. So some of these videos are going to be longer than usual, but It's important stuff.